Hi friends. Welcome to my channel. Please like the video and subscribe to my channel if you like the video. In this video we will study about the topic, limit state method of design, from the subject, design of reinforced concrete structures. Slide 1. In this slide we will see what is reinforced cement concrete. Reinforcing means forcing a material to stay within another material. Here steel is forced to stay with concrete. So, steel is the reinforcing material. Cement concrete is the mixture of cement, fine aggregate which is sand, coarse aggregate, which is gravel, and water. Any material added to concrete apart from the above materials is termed as admixture. Now we will see the materials used in the reinforced cement concrete in detail. Slide 2. In this slide we will study about our reinforcing material, steel. Steel is a ductile material which is readily available in the market. Ductility is the ability of a material to drag into wires. The different types of steel bars used in designing are mild steel and high yield strength deformed bars. Mild steel is of grade Fe 250. And high yield strength deformed bars, that is, HYSD bars are of grade Fe 415, and Fe 500. Ductility and tensile strength are the important properties of steel. Both ductility and tensile strength of steel depends on carbon content in the steel. As the carbon content in the steel increases, ductility of steel decreases and tensile strength of steel increases, and vice versa. Maximum carbon content allowed in mild steel is 2%. Slide 3. Now we will know about cement concrete. Cement concrete mix is differentiated as nominal mix and designed mixes. The nominal mixes of grades M10, M15, M20, and M25. The mix proportions of different grades of concrete as per IS 456 are shown here. For M10 grade of concrete the nominal ratio is 1:3:6. That is 1 part of cement, 3 parts of sand and 6 parts of coarse aggregate are mixed to get this grade of concrete. For M15 grade of concrete the nominal ratio is 1:2:4. That is 1 part of cement, 2 parts of sand and 4 parts of coarse aggregate are mixed to get this grade of concrete. And for M20 grade of concrete the nominal ratio is 1:1.5:3. That is 1 part of cement, 1.5 parts of sand and 3 parts of coarse aggregate are mixed to get this grade of concrete. Similarly, for M25 grade of concrete the nominal ratio is 1:1:2. That is 1 part of cement, 1 part of sand and 2 parts of coarse aggregate are mixed to get this grade of concrete. Design mix is a mix of cement concrete in which the ratio of materials are designed as per Indian standard codes, to achieve required strength. Next, we will see the concepts used in the design. Slide 4. In this slide we will study about characteristic strength of a material. Characteristic strength is defined as the strength of material below which not more than 5% of the test results are expected to fall. That means if we test a material, 95% of the test samples give strength greater than or equals to this value. If 100 samples are tested, 95 samples will give strength more than or equal to this value. Only 5 samples are expected to fail. That is, by considering allowable percentage error as 5%. Slide 5. Here, we will see about the characteristic strength of concrete. Characteristic strength of concrete is denoted with FCK. Nominal grades of concrete are denoted as M10, M15, M20, M25, M30, M35 and M40. In these grades of concrete, M stands for mix and number stands for characteristic compressive strength of concrete, when tested at 28 days. For example, if M20 grade of concrete is considered, its characteristic compressive strength, when tested at 28 days will be 20 newtons per millimeters square. That is, FCK is equals to 20 newtons per millimeters square. Slide 6. Here, we will see about the characteristic strength of steel. Characteristic strength of steel is denoted with Fy. Nominal grades of steel are denoted as Fe250, Fe415, and Fe500. In these grades of steel, Fe stands for ferrous, that means steel, and number stands for characteristic tensile strength of steel. For example, if Fe250 grade of steel is considered, its characteristic tensile strength is 250 newtons per millimeters square. That is, Fy is equals to 250 newtons per millimeters square. Slide 7. Stress-strain curve of concrete. This graph shows stress-strain curve for concrete. The factor of safety of concrete is taken as 1.5, as per IS 456. Only 67% of the characteristic strength of concrete is considered in design. Because the dimensions of the structural members and test sample are not analogous. On this we will apply our factor of safety. That is 0.67 FCK divided by 1.5, which gives 0.45 FCK. Slide 8. Characteristic strength of steel. This graph shows stress-strain curve for steel. The factor of safety of concrete is taken as 1.15, as per IS 456. Lower factor of safety for steel is considered when compared to concrete, because quality of steel cannot be altered once after its production. Whereas, the quality of concrete depends on quality of different materials such as cement, sand, gravel, and water used. The factor of safety of 1.15 is applied on characteristic strength of steel. That is Fy divided by 1.15, which gives 0.87 Fy. Slide 9. In this slide we will study about target mean strength of concrete. This is the strength which has high probability of getting values from test samples for a particular grade of concrete. The relation between target mean strength and characteristic strength is by using the formula Fm is equals to FCK plus 1.65 sigma, where Fm is target mean strength, FCK is the characteristic compressive strength, and sigma is the standard deviation. From IS 456, Table 8, the standard deviation values corresponding to different grades of concrete are shown here. Slide 10. Moment of resistance and bending moment. Moment of resistance of a structure is the maximum bending moment carried by that structure before failure. Bending moment is moment resisted by a structure due to the applied loads. Maximum bending moment for simply supported beam and cantilever beam subjected to uniformly distributed load over its entire span are shown here. Maximum bending moment for a simply supported beam subjected to uniformly distributed load over its entire span is given by W times L square by 8. N. Maximum bending moment for a cantilever beam subjected to uniformly distributed load over its entire span is given by W times L square by 2. We have to remember these values to design. Slide 11. This slide deals with the cross-sectional parameters of a structure. Cross-section means diagram showing the lateral dimensions of any structure. Here, there is a rectangular cross-section with breadth, b, and overall depth, d. The line drawn by joining locus of all neutral layers is called neutral axis. Above neutral axis the structure is in compression zone and below neutral axis it is in tension zone. The distance from top fiber to neutral axis is called actual depth of neutral axis, and is denoted as XU. Steel provided in the tension zone is denoted as AST. And the steel provided in the compression zone is denoted as ASC. The distance from the top fiber of the cross-section to the center of the reinforcement is called effective depth, and is denoted with small d. The distance from center of reinforcement to bottom fiber is called effective cover, and is denoted as d'. The minimum effective cover for different structures are shown here. That is, for slabs, minimum effective cover is 15 mm. For beams minimum effective cover is 25 mm. For columns minimum effective cover is 40 mm. For footings minimum effective cover is 50 mm. For footings underwater minimum effective cover is 75 mm. For pile foundation minimum effective cover is 75 mm. For lift wall or shear wall, minimum effective cover is 40 mm. Now we will know about design methods. Slide 12. Different design methods which we have are: 1. Ultimate load method. 2. Working stress method, WSM. 3. Limit state method, LSM. First, ultimate load method. In this method, the ultimate strength of the material is considered, which gives much slender sections for columns and beams, compared to working stress method. Working stress method, the stresses in the member is obtained from the working loads and compared with permissible stresses. Working stress method will lead to large factor of safety and oversized sections, thus the sections will be uneconomical. WSM is still being used in special structures such as water tanks, bridges, and chimneys, etc. Slide 13. Limit state method. This method is based on the concept of safety and serviceability. Limit state is a condition just before collapse. A structure designed by limit state should give proper strength and serviceability throughout its life. In limit state method, the limit state of collapse deals with safety of structure, and limit state of serviceability deals with durability of structure. Limit state method of design is explained in Indian Standard Code IS 456. Here we will try to study about limit state method of design. Slide 14. From IS 456 page 67, clause 35.1. In the method of design based on limit state concept, the structure shall be designed to withstand safely all loads liable to act on it, throughout its life. It shall also satisfy the serviceability requirements, such as limitations on deflection and cracking. The acceptable limit for the safety and serviceability requirements before failure occurs is called a limit state. The aim of design is to achieve acceptable probabilities that the structure will not become unfit for the use for which it is intended, that is, that it will not reach a limit state. Slide 15. As we know that limit state method of design considers both collapse and serviceability requirements of a structure. Limit state of collapse deals with designing a structure which is safe in flexure, compression, tension, shear, and torsion when subjected to factored loads. Whereas, limit state of serviceability deals with designing a structure which is safe in deflection, cracking, corrosion and vibration when subjected to factored loads throughout its lifetime. Therefore, here, we are designing the structure under collapse conditions, and check them under serviceability conditions. Slide 16. This slide deals with the considered partial safety factors of loads while designing. Partial safety factor is denoted with gamma F. The table is taken from IS 456, page 68, table 18. Both wind load and earthquake load have same effect on the structure. So maximum of the two effects should be considered by neglecting the other. This table gives the partial safety factor values for different load combinations under collapse and serviceability criteria. Now, under limit state of collapse criteria, partial safety factor of 1.5 is taken, for the combination of dead load and imposed load. Partial safety factor of 1.5 is taken, when dead load and wind load are combinedly considered. And partial safety factor of 1.2 is taken, when dead load, imposed load, and wind load are combinedly considered. Now, under limit state of serviceability criteria, partial safety factor of 1 is taken, for the combination of dead load and imposed load. Partial safety factor of 1 is taken, when dead load and wind load are combinedly considered. And, when dead load, imposed load, and wind load are combinedly considered, partial safety factor of 1, for dead load, 0.8, for imposed load and 0.8, for wind load are considered. In special cases like, stability against overturning or stress reversal is critical. The partial safety factor of 0.9 is considered for dead load while designing. For the limit states of serviceability, the values or gamma F, given in this table are applicable for short-term effects. While assessing the long-term effects due to creep, the dead load and that part of the live load likely to be permanent may only be considered. Now we will see the assumptions made in limit state method of design. These assumptions are discussed in the Indian Standard Code, IS 456, page 69. Slide 17. Assumption 1. Plane sections normal to the axis before bending, remain plane even after bending. That means the deformed shape of a considered section before bending and after bending are linear. Which is shown here. We are considering a section AB, before bending. This section has displaced from AB, to a dash, B dash. This displacement is linear. That is in the form of a straight line, as shown with blue color. Irregular displacement of the section is not as visible as in the black color, for designing. This assumption summarizes that the strain is linear after bending. There will be a layer in between top layer and bottom layer in such a way that it is neither subjected to compression nor tension. Such layer is called neutral layer. Here, we always consider compression as positive and tension as negative. Slide 18. This figure shows strain diagram for a rectangular cross-section, which is linear. The line joining locus of all the neutral layers in a cross-section is termed as neutral axis. Strain diagram before bending is shown as red line, whereas after bending is shown as blue line. The area above neutral axis is subjected to compression, and considering compression as positive. Strain diagram moves towards right. Whereas, the area below neutral axis is subjected to tension, and considering tension as negative. Strain diagram moves towards left. As the neutral axis is neither subjected to compression nor tension, there will be zero strain at neutral axis. Therefore, strain diagram for total cross-section is shown in this figure. Slide 19. Assumption 2. The tensile strength of the concrete is ignored. Concrete will also have some tensile strength, but when compared to steel it is not that predominant. Therefore, by ignoring the tensile strength of concrete, we are neglecting concrete in the tension zone. So, both the strain diagram and stress diagram of the cross-section are drawn, till the center of tension reinforcement only. Slide 20. Assumption 3. The maximum strain in concrete at the outermost compression fiber is taken as 0.0035 in bending. By this assumption, we are considering the maximum strain in the top fiber of cross-section as 0.0035, as area above neutral axis is considered to be in compression. Slide 21. Assumption 4. The maximum strain in tension reinforcement in the section at failure shall not be less than 0.002, plus 0.87 Fy, by Es. Where, Fy is the characteristic strength of grade of considered steel, and Es is the modulus of elasticity of steel. Modulus of elasticity of steel is taken as 2 × 10⁵ newtons per millimeter square. For all grades of steel. Slide 22. Assumption 5. The permissible compressive stress in concrete is 0.45 fck. Compressive strength of concrete in structure is assumed to be 0.67 times the characteristic strength. The partial safety factor of 1.5 shall be applied on addition to this. As the specimen casted for testing the compressive strength of concrete is in the shape of cube, and practically the shape of structure mostly doesn't exists, only 67% of the characteristic compressive strength value is considered, while designing. And, above this, a factor of safety of 1.5 is applied, which gives the maximum stress in the extreme top fiber of concrete as 0.45 fck. This stress diagram is also given in the code IS 456, page 69. By mirroring this diagram and rotating it to 90 degrees, we get our stress diagram. The center of force lies at a distance of 0.42 xu, from the extreme top fiber. So, the final stress diagram for concrete in compression is shown here. Slide 23. Assumption 6. The permissible tensile stress in steel is 0.87 phi. For design purposes the partial safety factor of 1.15 shall be applied for steel. As we know that, the characteristic compressive strength of steel is taken as Fy. By applying a factor of safety of 1.15 on this, the permissible stress in steel will be equals to 0.87 Fy. Steel in the tension zone is placed at only 1 point. So, the final stress diagram for steel in tension zone is shown here. Slide 24. These are the final strain and stress diagrams for the cross-section. On the stress diagram, compressive force, C, is acting at center of force, as shown in the figure. It is acting towards right, as compression is taken positive. Similarly, tensile force, T, is acting towards left at the center of reinforcement, as the tension is taken negative. Both the compressive force, C, and tensile force, T, are shown here. Slide 25. Now we will derive a formula for actual depth of neutral axis, XU. For this we are equating forces. If compressive force, C, is greater than tensile force, T, the cross-section will try to rotate in the clockwise direction. If compressive force, C, is less than tensile force, T, the cross-section will try to rotate in the anti-clockwise direction. So, for the cross-section to be in equilibrium, both compressive force, C, and tensile force, T, should be equal, as they are in the opposite direction. We know stress is mathematically defined as force acting per unit cross-sectional area. That is, stress is equals to force upon area. Therefore, force is equals to average stress times area. Compressive force, C, is equals to average stress times area. To find average stress, add both areas of rectangular part and parabolic part in the stress diagram, and equate it to a rectangle. We get average stresses in the compression zone as 0.36 FCK. Area in the compressive zone is B times XU. Therefore, compressive force, C, is equals to 0.36 FCK into B times XU. Similarly, tensile, T, is equals to average stress times area. T is equals to 0.87 Fy times AST. By equating both forces, we get 0.36 FCK into B times XU, is equals to 0.87 Fy times AST. By rearranging the terms we get XU, is equals to 0.87 Fy times AST divided by 0.36 FCK times B. This is the equation for actual depth of neutral axis. Slide 26. Moment of resistance from compression side. Moment is defined as the product of force and its perpendicular distance. Here, perpendicular distance is taken as lever arm, which is equals to d minus 0.42 XU. So, moment of resistance here is equals to compressive force, C, times its lever arm, which is equals to 0.36 FCK, B, XU times d minus 0.42 XU. This formula is used to find moment of resistance of a cross-section from compression side. Slide 27. Now, moment of resistance from tension side. Again, moment is defined as the product of force and its perpendicular distance. Here, perpendicular distance is taken as lever arm, which is equals to d minus 0.42 XU. So, moment of resistance here is equals to tensile force, T, times its lever arm, which is equals to 0.87 Fy, AST, times d minus 0.42 XU. This formula is used to find moment of resistance of a cross-section from tension side. Slide 28. IS 456 have suggested formulae for these stress block parameters. We can use any of the two formulae to find stress block parameters. The formulae from IS 456, page 96, and derived formulae of these parameters are shown here. This is the end of this topic. Please like the video and subscribe to my channel if you like the video. Also comment about the video. Thanks for watching.